Okay, my people, we are back. We were kind of finishing up this slide in here, talking about um, how this chi-square statistic is going to give us a p-value and what that means in terms of whether or not the M&M's company are telling the truth or not. Essentially, when this number is really big, it's going to give us a very small p-value, which is going to get us to reject the null. If this number is really small, that's really meaning that all these values are really, really close together. And that's evidence that we're going to fail to reject the null, that the company is telling the truth. Okay. So, Mr. Keys, I don't want to do all these calculations. I failed Algebra 1. Yeah, I'm right there with you. So is there a better way? Yes. Hang on tight and listen very carefully. I don't have any visual slides, but you want to pick up your TI-83 calculator right now. And what do you want to do? Well, we want to put this data in here into two lists. So you want to go to Stat, Edit, and list one, you want to put in all the observed values. There's 6 of them. Then you want to go over to list two and put in all the expected values. Please do not round here. Make sure you're very exact. All right, so once you have the two lists in place, list one and list two, your calculator is going to be your best friend to not only find this chi-squared statistic, but also give you the p-value. So how do you do that? Well, we want to go to Stat, go over to the tab that says Tests, and then go all the way down, and I mean all the way down, near the bottom, where it says chi-squared GOF test. So chi-squared GOF test, it's going to prompt you for a few things. One thing it's going to prompt you for is the observed list. You want to make sure it says L1. The expected list, hopefully that was in L2, you put in L2. And then it prompts you for degrees of freedom. So we haven't talked about the degrees of freedom yet. In this case, the degrees of freedom is 5. Why is that? Well, there are 6 different choices of this categorical variable. And so the degrees of freedom will always be the number of choices you have minus 1. So in this case, there are 6 colors. 6 minus 1 is 5. So you want to put degrees of freedom 5. Then you want to go hit calculate, and then boom, this is awesome. So you're going to confirm that they're calculating the chi-squared to be exactly the same. My calculator says 10.1799. It's a little more exact. And it's giving me a p-value of 0.07. So let's go to the next slide and see how they are finding the p-value by using a table. So before we get there, there's some other characteristics of these chi-square distribution graphs that you should be very familiar with. So I'm talking slower for a reason. One, they're all going to be right skewed. Chi-squared can never be negative. And it's pointing out here the degrees of freedom is the formula that I just mentioned. It's the number of categories minus 1. So in this case, we had 6 colors. 6 minus 1 is 5. Okay, so they give you 3 examples here of 3 different distributions, which are not ours. These are the distributions for different degrees of freedom. Notice our degrees of freedom are 5. So try to see if you can see a pattern in here. So this apex of this curve gets pushed further and further to the right when the degrees of freedom go up. And I really want you to notice one more pattern, which is very difficult to see. If you take the degrees of freedom and subtract 2, that is where the apex of the curve is going to be. So in this case, if the degrees of freedom is 8, 8 minus 2 is 6, that's where the apex of the curve is. This is degrees of freedom 4. So if you go 4 minus 2 is 2, notice the highest peak in here is at 2. So let's go to the next slide and see our graph in here. So notice this is the graph of our M&M example, and we know our degrees of freedom is 5. So when you sketch this out, you're not just like nonchalantly just graphing any right skewed graph, the apex in here is really corresponding to how many degrees of freedom we have. So in this case, degrees of freedom is 5, so 5 minus 2 is 3. So you can see if I go up from 3, that is where our apex of the curve is. That's the highest point. And then we know it's going to be right skewed. So this is our chi-squared value. It's at 10.18, which is our line in the sand that's going to produce a p-value. And the calculator did all the work for us, and it found a p-value of 0.0702. And so they're going to be using a table. This is table C, and table C is used by knowing the degrees of freedom. And then notice that table C is very limiting. It's not going to give you an exact probability. It kind of gives you, based upon the chi-squared statistic being somewhere trapped between 11 and 9 in here, ours is 10.18, then we can conclude the p-value is going to be somewhere between 0.05 and 0.1. So that makes sense because our calculator just told us the very exact value. Our p-value was 0.0702. So that's the p-value that you're going to be able to conclude at the end here. Notice by using table C, our p-value is somewhere between 0.05 to 0.10. It is greater than the significance level, for example, alpha of 0.05. Therefore, we reject the null. So the same principles of significance tests that we've learned before in the past apply here at the very end. When we have our p-value, when we have our alpha level, we make that same type of conclusion. So what does that mean when the p-value is greater than the alpha? We don't have significant evidence to conclude that the company's stated color distribution is incorrect. So yeah, each color was off, some were bigger, some were smaller, but in the end, it wasn't a significant difference. So we are taking into account all colors in here, and that's why it's called a goodness of fit test. Okay, so let's move on in here. One thing I didn't make mention is uh, this color distribution right here is not valid for um, for just any situation. We do have conditions, and I went a little too fast in here. It says when the expected counts are all at least 5, then that sampling distribution is going to be close to that chi-square distribution that we're talking about in here. So keep in mind right now, all expected counts, not most of them, all of them have to be at least 5. So that is our segue to our conditions, our 3 conditions, and here they are. The first condition, just like normal, excuse me, just, I didn't want to use that word, just like in the past, random comes from either a well-designed random sample or from a randomized experiment right there, basically an SRS. So we want to be picking out a bag of M&Ms from a random sample, okay? The 10% condition. So when sampling without replacement, check that little n is no more than 10% of the entire population. And the last one is really the newest one, the large count condition. All expected counts have to be greater than or equal to 5. So when that occurs, then we can use our chi-square distribution and find our p-value. Okay. It's giving some warnings here that I've already made mention. The chi-square test statistics compares only the observed and the expected counts. Do not try doing this with the proportions. Be warned. When checking the large sample condition, again, be sure to use the expected counts, not the observed ones. These are common mistakes people use. Okay, so this was a summary of what we just did, the hypotheses, the chi-squared, and so forth, and we found the p-value. Okay, what we're about to start right now is a 4-step process for a totally different example. We haven't been through the 4-step process yet for goodness of fit. We've been through an analysis of, oh, what does the hypothesis look like? What does the do step look like? What does the conditions look like? But we're going to use a totally different example here, going step by step for estate plan do conclude. So the problem is about this book that suggests that a hockey player's birth month has a big influence on the chance they make it to the highest levels of the game, meaning the professional league, the NHL. Specifically, since January 1st is the cutoff date for youth leagues in Canada, where many NHL players come from, players born in January will be competing against players up to 12 months younger. So that means they have an advantage because at that young age, if you're 7 years old and you're a full 12 months or 11 months older than someone, you're faster, typically faster, stronger, and so forth. And if you were born in December, that might lead to you going, oh my God, I'm playing with such older kids. It's not fair, and I'm not as fast, I'm not as coordinated, and those kids might end up quitting because the big kids are bigger, faster, stronger, and so forth. So the theory here is older players tend to be bigger, stronger, and more coordinated, hence get more playing time, more coaching, and have a better chance of being successful. To see the birth date in a related success, judged by whether a player makes it to the NHL, what did we do? We took a random sample of 80 NHL players and we recorded their birthdays. So what would that look like? Well, here we go. Here's our 80 players. These are not expected. These are observed counts. Out of our 80 people, we had 32 observed in the months of January through March. We had 20 in these months, we had 16, and then 12. Notice these numbers keep on getting smaller and smaller and smaller. I wonder if this book's theory that people born in the earlier months of the year do have an advantage. So the question is, do these data provide convincing evidence that the birthdays of NHL players are evenly distributed among the 4 quarters of the year? So step one is to write the hypothesis. That's to state the problem. So what is the stating of the problem? Notice we're describing it in words. So the null hypothesis is the birthdays of NHL players are evenly distributed among the 4 quarters of the year. So since there's 4 quarters of the year, this is 25%. We would expect 25% of all the players come from this range. 25% come from here, 25%, 25%. That is the null hypothesis, meaning his theory is not true at all. The null hypothesis is everyone is coming from a month. The birthdays have nothing to do with the situation here. Um, Everything's evenly distributed. The null hypothesis is claiming that the birthdays are not evenly distributed among the 4 quarters of the year. And so we always state our alpha level, and that is 0.05. That's the same as before. So that's the first of the 4 stages, state. Okay, here's our plan. The plan is, if the conditions are met, we're going to perform a chi-square test for the goodness of fit. That is the official name of this test. And then we have 3 conditions to be met. One is the random condition. The data come from a random sample of NHL players. And the next one is a 10%. Well, we just have to make sure that 10 times 80, 800, is less than the population of NHL players. And we just nicked it, um, um, meaning 800 is a little bit less than 879, which is the total population of NHL players. And then finally, this where it's different, do not use observed counts, use expected counts. So we have to make sure that each of those 4 regions, those 4 categories, meaning January through March was one category, April through June, I guess, is the next one. If the birthdays were evenly distributed across the 4 quarters of the year, then what should we expect with our 80 people? Well, 80 divided by 4 is 20, so that is actually the expected count for each and every single category right there. Notice, even though we got 32 observed, we're expecting this one to be 20, 20, 20, and 20. And for all 20, 20 is the expected of all four of those categories right there. Oops, I went a little too fast. So since all these categories are at least 5, meaning the expected one, we are good to go. So that is 2 of our 4 steps in here. So state plan, the plan is those 3 conditions right there. Let's stop this video and continue on in a little bit.